Good morning and welcome to the second day of the 2021 ASFPM Annual Conference. We're so glad you could attend this event. I'm Meg Galloway, your moderator for session D3, Modeling Flood Warning Systems. This is a very timely topic as much of the country continues to experience more frequent and severe flooding events. And we have a great lineup of presentations and speakers for you on this subject. However, before we start, I want to go over a few housekeeping items. After I introduce the speakers, we will watch for a presentation. We watch that presentation. Each one is around 20 minutes long. Then we'll use the remaining time to answer as many questions as possible from you within our 30-minute window for the presentation. Asking questions is easy. Just use the chat box at the right side of your screen. Please put your questions in as you think about them so others can see them. It may take a minute or two for them to appear back in the chat box. If you see a question from someone else that you like, hit the thumbs up button, and that will help catch our attention that many people think this question is important. And I can't encourage you enough to get your questions in there early. With that, let's get started with learning more about modeling flood warning systems. Our first presentation is FIMAN-T, North Carolina DOT's response tool for managing flood impacts to transportation assets. The session will be presented by David Key with co-presenter Matthew Laufer. David Key serves as Director of Water Resources, Hazard Mitigation, and GIS Services at ESP Associates and has over 29 years of experience. The focus of his entire career has been watershed, hydrologic and hydraulic modeling, FEMA flood insurance studies, flood mitigation, GIS application development, and flood warning application development. He has served as project manager for the North Carolina Flood Mapping Program for 20 years. His recent focus has been in the development of flood warning applications, including FIMAN, FIMAN-T, SARA, and the flood warning application for the city of Roanoke. Take it away, David.
Good morning, everyone. Thank you for joining me. My name is David Key, and I'm with ESP Associates, and I'm also joined here with Matt Laufer with NCDOT Hydraulics. This morning, we're going to talk to you about a very exciting project we've been working on for the past few years called FIMAN-T. It's NCDOT's response tool for managing flood impacts to transportation assets. I've got a lot to dive into here, so I'm just going to get going. A quick roadmap of our presentation for you. I'm going to do a little bit of an introduction, a little bit of history of FIMAN and how it born FIMAN-T. Then I'm going to talk about and do live demos, so please bear with me and say a little prayer for FIMAN-T. One's based on gauges or real-time readings, and another one's based on the predictive hurricane storm surge information. I'm going to talk a little bit about ground truthing and how we've been able to validate this data, and then some steps, next steps for the future as we conclude. So very exciting, and I hope you get a lot out of this. Number one, some introduction. For those of you familiar with FIMAN, this may be no news to you, but North Carolina's FIMAN system stands for Flood Inundation Mapping and Alert Network. That's FIMAN. This system's actually been around since 2013, but really it was rewritten in 2015 and 2016, and it's been a public site since then. Very instrumental in the last 4 to 5, 6 hurricanes that have hit us since 2016. Site's made up about 450 to 500 sensors across the state that are measuring rainfall, mostly stream stage and coastal surge modeling. The site provides real-time and forecasted flood inundation and building impacts and summary reports, as well as text and email alerts for users. A big thing happened in 2018 that gave the thought behind FIMAN-T. We had 2 of our major highway corridors in our state go underwater. On the left side of my screen, you see Interstate 95 on the southern end of our state in the city of Lumberton, North Carolina. Interstate 95 went underwater and was basically closed for about a week. It topped over the bridge there on the Lumber River and really shut down transportation in our state on this very important north-south corridor along the eastern seaboard for about a week. At the same time, in the eastern part of our state, Interstate 40, which crisscrosses our state from east to west, but most importantly connects our state's capital with the coast and is an important evacuation corridor, it was also underwater in the town of Wallace. Interstate 40 went underwater by about 4 feet of water and was basically shut down for a week. The graphic you see at the bottom, or the movie you see at the bottom, is really compelling imagery from the event that sticks with me. This is a cleanup crew following, where they're washing off dead fish after the water receded off of our most important interstate in the state. So obviously NCDOT was put in a position where they really wanted to use some of the data to never let this happen again, or at least know about it when it was going to happen. So some of the things that was the objectives of FIMAN-T was a collaboration of work between NCDOT and North Carolina Emergency Management. And the main objectives was to leverage the existing investment in data, the LiDAR data, the roadway data, the FIMAN infrastructure and the database, and all the lessons learned from developing the inundation mapping tool for the past 2 decades. Put that together to give DOT actionable information on when roads were going to flood, when they're going to be clear again, and how the bridges are performing hydraulically. Software was going to be built on the FIMAN network, so it's a proven platform. We were just going to stand up a database alongside of FIMAN, but not be in the way of FIMAN for emergency response. In 2019, we did a pilot on FIMAN along the Neuse River, where we tested and developed the FIMAN functionality and the database, and rolled that out on a non-public development server. The next year, 2020, we rolled out expansion. We developed new data for 35 plus odd sites, developed the coastal tools for the surge, which I'll show you later on this morning, and lots of other functionality, including exports and other reporting tools. The backbone of FIMAN-T is data. As part of Hurricane Florence, we developed as part of the response to Hurricane Florence, we developed a statewide LiDAR 3D road elevation. What you see on your screen now is not a digital elevation model for North Carolina. It is the 3-dimensional rendering of our road network, some 80,000 miles down to the pixel level with LiDAR-derived elevation data. I'm going to zoom in a couple times and show you some pilot data. What you see there in color-coded is just a slice of our road network, a 3D road network. I'm going to zoom in just to show you the level of detail that we have down to the street level. This is the backbone that drives FIMAN-T. So now I'm going to dive right into the application and give you a little demonstration of how it's used and some of the functionality. So this is FIMAN-T. It is a password protected non-public site. So we authenticate using a system called NCID, where users are given authentication via that secure login with user ID and password. Once they're in, they get to a home screen that looks just like this. You've got your basic map functionalities, your zoom, your home, your find me, your base map picker. You've got some controls to show things like weather radar. You can filter data by NCDOT divisions or river basins. You can search. It's got a legend. All of the active sites are color coded by the current condition. So on a day like today, it's sunny, it's beautiful. It's pretty boring day to demo FIMAN, but I can change that. We've got a test sites set up for an exercise that EM and NCDOT recently completed. And this site is emulating what FIMAN-T will look like during a flood event in the east. So we've got 6 sites in here along the Neuse River, and I'm going to demo some functionality of FIMAN-T using this site. So you can see this is simulating Hurricane Fran back in 1996. And this simulation was set up for the exercise, assuming it's September the 12th, 1996. At that day, the river was cresting in Goldsboro and still rising downstream of there. So I'm going to use this test case scenario just to show you the power and how FIMAN-T is used by emergency responders during an event. So in order to interact with these sites, you simply click on it. Click right here and you're going to go into a dashboard for this site. So I'm at Neuse River at Kinston, pretty big river down here and a very flood prone community. I'm going to turn a few things off now to make it a little bit cleaner. So what you're going to see is a dashboard. This floating dashboard has 4 tabs. I'm going to walk you through each one of these tabs. The current tab is pretty self-explanatory. This is going to show you current conditions on the map, and it's going to show you current conditions in these information widgets down here. So right now, in this scenario, it's September the 12th, it's noon, we're peaking upstream and we're still rising down here in Kinston. It shows you the blue area is the inundation under current conditions. And these color-coded roads are much like the color-coded buildings in FIMAN, except it deals with flooding over roads. We've got a legend on here, and the roads are color-coded by depth of water over them, anywhere from 0 to 5 feet, which is a yellowish road, all the way up to 5 feet inundated, which is a purple road. Our bridges show up with color codes as well, showing their condition. Right now, all you see is green, so that means that the water is not within 1 foot of the low chord or low steel of the bridge. Assets show up as a NCDOT assets show up as a red triangle on here. This next widget, working from left to right, is the hydrograph. This shows you everything to the left of this line is past events and past stage. This is color-coded by severity, and everything to the right of this line is the forecasted information. And I'll come back to that. This tab in the middle shows you the historic peak at this gauge. We're at 19.1 here, but the historic peak on this was Hurricane Matthew of 28.3. These next 2 widgets over here on the right side deal with NCDOT assets. The first one is showing the summary of impacted roads. Right now, this shows that we've got about 1 mile of roads impacted, but all of those are local. This widget can be interacted with by clicking on it, which will pull up a table that shows an overall summary, itemized by road type and depth of flooding. Also, it has another tab in here that shows every segment. This shows every segment, so there's 61 segments of road impacted right now. These can be sorted, they can be filtered, they can be queried, and each one of these, if you click on it, it'll zoom you to that road segment and show you the impacted roads. The next tab is the bridges. This will pull up a table of all of the bridges, and it will show the road name, the road elevation, the low chord elevation, the current flood elevation based on our modeling and sensors, and then the freeboard. These are sortable tables. The next tab I wanted to show you is really how this is used. It's a forecast tab. When you click on the forecast tab, we know we're still rising here, so we want to see how bad is it going to get in Kinston. You click on forecast, the map really doesn't change, but the dashboard changes. So now we're presented with a time bar slider or a forecast slider that has 2 axes. The lower axis is time from now, and the upper axis is the river stage based on the forecast. So really what you're looking at here is a visualization of this side of the chart. So we start out red and we go up into purple and we end with a peak of 23.3 5 days from now. Now, how do you use this slider? You could use this slider by either picking a time, say you want to see what it's going to be in 48 hours. So you can just come right here and click. And the map will show you within 48 hours, your inundation is going to look like this. And these are the roads that are going to be impacted. And these tables update. So in 48 hours, you're going to move to 1.5 miles. Not a big difference. But so you say, what's it going to look like at the peak? Well, you're going to come in here and slide it all the way over, and you're going to see the inundation and the road impacts at the peak. From here, you would go in and see that we've got 1 state highway that is going to be impacted. So I'm going to use this tool to figure out where it is. I'm going to click here. I'm going to click on my road segments, and I'm going to use this filter here to filter by state highway. That's going to show me that I've got segments of highway 11 in here that are going to be flooded. I'm going to click on this. It's going to take me in. And this section of Highway 11 is going to have about 4 feet of water on it in 5 days. So a very, very powerful planning tool. Another tab is the scenario tab, which this is pretty self-explanatory. The scenario tab allows the user to play, to do what if scenarios based on a variety of flood stages and river heights at a given flood stage, what roads are impacted and what bridges are going to, what the states of the bridges are going to be. So it's a very good tool. My last tab is the historic tab. This is a brand new feature that we added to FIMAN-T this past month, and it's probably one of my favorites. If I click on historic, well, let me preface that when we're, during a flood event, a lot of times you get a lot of questions on how does this event compare to past events. A lot of folks in the eastern part of our state want to compare to either Matthew or Hurricane Floyd or Hurricane Fran. So when you click on this historic tab, it's going to query a database that will pull up the maximum flood of record for this particular site, which was Hurricane Matthew in 2016. And so the table is going to show the stage from that event. The inundation is going to be the inundation from that event. And the color-coded roads are going to be the actual DOT asset impacts from that event. So if you want to see how this compares to how Hurricane Matthew compares to, say, Hurricane Florence, you just select it in this table, and the map will automatically change to the maximum extent from Hurricane Florence and the impacted roadway from Hurricane Florence. And the last thing I wanted to show you is an export tools. In the upper right corner of the dashboard, there's a download KMZ button. From this tool, you can click on that. It's going to give you a little bit of instructions on what to do when you download it. And then it's going to download a KMZ, which is a grouping of the inundation layer that you have on your screen now. It could be the forecast, it could be the current, it could be an historical event. And it's going to group those together and create a Google Earth KMZ that you could either download, email, or pull up on the screen and not have to be inside FIMAN-T. So there's the inundation extent from Hurricane Matthew. And this data comes across SMART, where it pulls the attributes of the road, like the maximum depth and the road name. So really, really cool way to export data. So that's pretty much it for the gauge site. Now I want to talk about the storm surge site. This begins with a system called CERA, or the Coastal Emergency Risk Assessment. This tool, with an approaching hurricane in the Atlantic, we're able to download the results of ASFPM modeling for that event that contains GIS layers of the forecasted peak inundation. We've developed some tools to extract that data with every time an advisory is updated, and that data is downloaded and processed. We process that data with the LiDAR data to develop a 3D inundation map. We also process that data with the statewide 3D road rasters that I showed you in the other slide to develop FIMAN-T data to support response to storm surge. So what happens is, during an event, the site updates every 6 hours with a new inundation map based on that hurricane center track and the estimated impacts to the road network from that inundation mapping. So it's so every 6 hours, the map service updates inside the SERA module of FIMAN-T. So I'll switch over to that now and just show you a demo of that. So at the upper left-hand corner of this, you got two modes. You got gauge-based and SERA surge. Right now we're in gauge-based, so you see all these gauges. If I click over to SERA surge, I'll get a disclaimer, and I can hit accept. Well, today's a sunny day. We don't have an approaching hurricane, so nothing's going on. But if there were a hurricane out there, you would see the track, you'd see the last advisory track, you'd see the inundation mapping and the roadway impacts from that one. But what I can show you now is something really cool that we added. We added these past storms. When you go in here, you can choose a year event, and we've loaded 5 different past hurricanes in here. Hurricane Fran from '96, Matthew from 2016, Florence from 18, Dorian from 19, and Isaias from 2020. So say I want to see what the storm surge looked like from Hurricane Florence in 2018. I'll click the year 18, and I've only got one in there for 18. The map will change and it'll load the inundation polygon for Hurricane Florence. It'll load the track for Hurricane Florence. Down here will be a summary table showing how many miles of roadway were impacted by that storm surge. So it's a lot, it's 1,670. And then the tool is set up to allow visualization of not only that storm surge from Hurricane Florence, but the impacted roadways. This is what it would look like also with an approaching event. So you see down here in Carolina Beach, the inundation mapping from that hindcasted data. And you can also see the impacted roads. A really cool use of this tool is a what if scenario. So if say I want to compare the inundation mapping from Florence in 2018 to what happened in 1996 from Hurricane Fran, I would just stay in this view, change it over to another event, and pick Hurricane Fran. And you start to see the differences in impacts. So this is the Hurricane Fran inundation mapping, and I can change that back to Hurricane Florence. So it's a really, really good tool as a storm is approaching. A lot of times you get the question, well, how's this going to compare to Fran? Or how's this going to compare to Floyd or Matthew or Isaias? It's a really, really powerful tool that we're really proud of. And lastly, I'll talk a little bit about validation. We've had the chance to test some of this tool with recent flooding events, and this is just some examples of some ground truthing, we call it. This is out in the Neuse River back in February of last year. The tool was reporting freeboard of about 1/10 of a foot. This was taken about the same time that was taken, and we measured about 6 inches. So that's not bad 4 miles from the gauge to know that you're that close. So we were really pleased with this validation. Here's another one that I'm really proud of. This is also along the Neuse River. This is the inundation on February 12th at 9:15. These color-coded roads were supposed to be underwater. We sent crews out in the field, and I was standing right here looking this way along Slick Rock Road, and this is what I saw. The system was showing about 1.5 feet of water over the road, and just so happens this truck drove by and gave me a really good validation point for that road inundation there. So we're really pleased with how this data came by. This was about 6 or 7 miles from the gauge, which showed very, very accurate data. And lastly, some of our historic data we compared. This is the high water mark or the historic flood inundation from Hurricane Floyd way back in 1999. So you see the blue area is the inundation extents of the 99 event. And I found this old picture. This was the intersection of Candlewood Road and Steeplechase Road on September 16th of 1999. The FIMAN-T data said that Candlewood Road had 7.1 feet of water on it during the peak of the event. And this validates really well with about halfway up that stop sign. So we're really pleased with that validation as well. Lastly, I'll talk about our next steps and where NCDOT is going in the future with this. NCDOT completed a build-out plan for FIMAN-T, prioritizing hundreds of sites for new gauges to be installed and also FIMAN-T products to be developed. We're developing lots of new functionality to FIMAN-T, including some reports to help with the battle rhythm during disaster events and hurricane flooding and other types of flooding. We're also have this stood up on emergency management's staging server for hurricane season 2021, as well as a redundant instance at ESP server over here where the storm surge module will run. We have some pilots planned. We have a pilot plan for integrating the national water model into FIMAN-T to supplement the sites that do not have a forecast. We've been developing some logic to pull the national water model forecast and do the inundation mapping on that, as well as a cost and impact analysis pilot study where we're going to look at inundated roads and the temporal aspects of how long those are inundated and what those costs are to transportation and also maintenance of the roads. Speaking of maintenance, there's a lot of maintenance to be done with the LRS network of the roadways, the DEM maintenance to be done, the model maintenance to be done, and lots of other software and database updates. So in conclusion, 2018 proved that, even our most resilient highways like Interstate 95 and Interstate 40 are prone to flooding, prone to closure, and information is going to be powerful. And knowing how to answer questions is the name of the game during one of these events. Knowing how to answer the question, what roads are going to be underwater, knowing how to answer the question, when's those roads going to be clear, knowing how to answer questions, do we need to inspect those bridges? Do we need to close those roads? This is all powerful information, and really, really, really proud to be a part of it. And I can't wait to see where we go for the next few years in this state. I want to thank you for your time, and we're here standing by with any questions.
David and Matthew, thank you for that very informative presentation. We've got a lot of questions, so let's get right to them. The first one, a lot of people want to hear the answer to: how operationally does FIMAN-T get used by North Carolina DOT? And is it integrated with EOC workflows, tools, and other platforms?
Yes, I'll take that one, David. So NCDOT is working closely with our emergency management, emergency operations center during these events. So this year is one of our first years to really implement the full suite of tools. So we're working with them. We had a couple exercises this spring, and so we're going to be integrating that with the EOC. And then internally, we're working with our division engineers and our staff in the field to operate the tools. So we actually have training next week on that. And we're also just putting together some executive reports that will come out during the events, during like at 8 o'clock in the morning and then 5 o'clock in the afternoon, and then for other briefs that go on. But we're still working out the actual reporting to executive leadership, as well as the governor, and then other entities that will be using the tool.
Thanks, Matthew. Our next question: what is the source for your forecast data?
You want me to take that, Matt?
Yeah, that'd be good, David.
Yeah, that's a great question. We're getting two types of data. We're getting the past data, obviously, from the USGS, from North Carolina Emergency Management's own gauges, but the forecast comes from the Southeast River Forecast Center. And there's a program that runs in the background that makes data calls into that, and the data for the forecast is returned in an XML format, and it all goes into a database, and that is updated every 15 minutes. That's from the Weather Service, NOAA's River Forecast Centers.
Great. Next one: what is the underlying hydrologic and hydraulic software?
Matt, do you want me to take that one?
Yeah, please do, David. Thanks.
Yeah, that's very easy. Each one of these sites has H&H modeling behind it. The riverine sites, the H&H is a HECRAS model, one-dimensional HECRAS model that extends several miles downstream and several miles upstream for the extent of the libraries. And so those models are pre-run in the background for a library of flood elevations every half foot, or sometimes even every quarter foot.
Great. Got a few more minutes, so let's keep going down the list of questions. Does FIMAN-T provide automatic alerts to the staff with at least 24 hours notice, or does the system require a monitor?
The system runs automatically. It runs 24/7. Alerts are currently built into the FIMAN system. Those are alerts based on text messaging and emails. We are currently doing alerts in FIMAN-T for road segments and for bridge conditions for DOT. Those will be in the next version this summer before this hurricane season.
Great. Our next question is, since this is a website which is still secure and private, how can this information be accessed directly by the public? Would it be useful to connect with Google Maps? This could help with the Google Maps not directing cars through those specific roads before and after an event.
Yeah, Meg, that's a great question. I think we're testing this. Our preference is to have this supplied on our Drive NC app, which is our transportation, mobility, and safety website that, basically would, identify what roads are closed and that type of thing. So we definitely want to get some visuals on the data coming from FIMAN-T, and understand the data better and get, a level of trust with it as we move forward. But as David showed, there's a pretty good level of trust, but we still need to get that visual on that before we produce it. So with our Transportation Operations Center to get those validations and push that to the Drive NC system.
Good. Hayden's asking, what is the basis of the modeled inundation at the gauge stations? How are the different floodplains determined?
The basis is a one-dimensional HECRAS model, and the flood elevations are determined with a range of discharges that are input into that model, matching that elevation exactly at the gauge every half foot or quarter foot. And then that information is mapped on the QL1 LiDAR data for the inundation extent. All of that stored in a SQL database for quick retrieval.
Good information. Can your system actually display real-time flood extent, for example, from a satellite using radar or other technologies?
No, we're not showing any information from radar remote sense data, but the having it be based on an actual gauge measurement tied to the accurate high resolution LiDAR, in my opinion, it's much better and much faster than waiting on those remote sensed imagery.
Good. Lori wants to say it's an amazing tool. Can you talk about how you maintain and expand this tool? How many developers, staff work on this product, for example?
Matt, you want to take the first part of that?
David, why don't you go ahead with the developers, because I think that's an important part of it.
The question to that is less than you would imagine. A team of 2 developers. The product is mostly in the data. There is a lot of data maintenance in it with the road updates and for FIMANs on the building updates. But the system's been around for 15 years. And fortunately, emergency management and teaming with NCDOT is going through and updating, extending the libraries, updating them with more up-to-date models and better topography. But as far as the developers, 2 developers and a lot of GIS folks making the data. And engineers doing the modeling.
And then the second part, where does your funding come from?
That's a great question. So this past year, we got a lot of funding from the General Assembly in North Carolina, and then DOT also supports the efforts internally. So the FIMAN-T product.
Okay, I think we have time for one last question. Are there services that FIMAN-T offers for consumption or an API to connect to analysis results for other data streams?
Do you want me to take that, Matt?
Yeah, that'd be good. Thanks.
That's a great question. Yes, everything you see on the website is definitely based on services. They are secure, password protected services. And the way the data is served, you can imagine all the inundation layers and the roads are stacked feature classes. So yes, everything's based on services, but as of this time, they are locked down secure services.
Okay. Well, that's all the time we have for questions. There were a lot more good questions that we couldn't get to, and I'm sorry if your question can't be answered or we weren't able to get to it. But we do need to go on to our next presentation, which is Feed the Machine, Flood Response Automated Predictions to Improve Emergency Planning. This is going to be presented by David Leone with a co-presenter, Daniel Purdue. Mr. Leone is a hydraulic engineer and associate principal at GZA Geoenvironmental Incorporated. He leads GZA's Dam and Water Resources Technical Practice Group. Over his 20 plus years in the engineering field, he has specialized in hydrology, hydraulics, natural hazard and climate change vulnerability assessments, and design of flood mitigation structures. David is also a licensed professional engineer in 4 states and a certified floodplain manager. Mr. Purdue has extensive experience in all aspects of geospatial technology as a certified GIS professional. He brings over 30 years of combined CAD and GIS experience in data management, data development, spatial analysis, cartographic design and production, and field data collection. Mr. Purdue serves as Geospatial Systems Lead and heads the Geospatial Solutions at GZA and manages the GZA's ESRI partnership program. So David,
Good morning.
ready to go.
Today, we're going to be talking about feeding the machine, flood response automated predictions, and improving emergency planning. I'm Dave Leone. I'll be joined later by my colleague, Dan Boudreau. Before we get started, I'd like to provide a brief acknowledgement to the folks at the RISE Resilience Innovations Urban Mobility Challenge for partially funding this work, in addition to GZA's own innovation program. Here's today's agenda. I'll start off with a quick background, talk about the problem we really are focusing on, the emerging solutions that we and other folks are working on, and we'll leave you with some takeaways before we answer your questions. There are a variety of flood mechanisms. Today, we'd really like to focus in on local intense rainfall, which you might also know as urban flooding or cloudbursts or even rain bombs. This is an emerging flood mechanism. Worsening due to climate change, and we feel like it needs a little bit more attention as compared to the river and stream or storm surge flooding, which is very well forecasted and predicted in advance by the National Weather Service. The most famous recent example of an intense rainfall event was perhaps Hurricane Harvey, which really hit the area of Houston, Texas, southeastern Texas very hard. The general problem, as you know, is when intense rainfall falls on an urbanized area, it can overwhelm a drainage system and cause very deep, intense, periodic flooding issues for the community. This type of flooding is localized and highly variable. It has limited warning time. It can be unexpected because it's off-stream and result in high impact potential because it tends to flood areas of high population density. It can result in uninsured losses, and it's likely to get worse in the future. And to that end, this is a quick snippet of some of the climate change projections. You can see, depending on where you are in the country, the one takeaway is that extreme precipitation is likely to go up in intensity, and that's a result of the increase in weather extremes that is becoming more prevalent as a result of climate change, both in terms of days without precipitation, but also in days with very heavy precipitation, and that is happening at the expense of the days in the middle of moderate precipitation. So we'd like to focus on a particular example problem. This is an intersection in Norfolk, Virginia. And again, we thank folks from RISE, Barbara Walker, for the photo. This photograph shows you what the problem is in one very nice image. Here we are looking at a road that has been flooded due to intense rainfall. We have somebody who's driving through that road, which is a risk to life. There's a communication challenge in that this driver didn't know the road was flooded or decided to drive through anyway. Either one is a communication challenge. It results in business disruption. Kogan's Pizza here, this building in red, probably did not have as good of a day as it was hoping as a result of this flood condition. And it can also result in some property damage. Traditional solutions to this kind of flooding are to rely on weather forecasts and observational flood data. You may also get flood warnings shared via multiple media platforms. People may just know in the town that, oh, that intersection always floods when you get this amount of rain. Pre-event modeling and inundation mapping, that's what we rely on for things like coastal flooding, even for dam failure flooding, thinking of emergency action planning there. But there are challenges when it comes to applying these traditional solutions to the local intense rainfall problem. Firstly, the highly localized variability and limited observations associated with a rainfall event challenge the weather forecast solution. Flood warnings shared via multiple media platforms can create some false alarms. Local impacts are hard to convey by mass media. Institutional knowledge can be a problem because you need to have generational transition. You also need those personnel who are familiar with the experience of the area available during a particular event. Pre-event modeling and inundation mapping, the challenge there is long simulation times, and also the limited accuracy of forecast data. So the emerging solution that we're working on is basically a three-step process of collecting information, using that information to forecast the extent of the problem, and then to act on that information through communication, planning preparation, and response. Today, we're really going to focus in on a couple of specific areas. Those include forecast precipitation, high resolution modeling and processing, and then how to get the word out through different communication platforms. So let's start off by talking about forecast precipitation. What we want from forecast precipitation data is accurate information as much in advance as possible. The challenges with that are that the accuracy of a local intense rainfall prediction is highest with the shortest advance warning time. The temporal resolution can also be a problem because these events are so localized. Integration into GIS can be a challenge. We're not going to get into that today, but the formats of these models and how they fit into a GIS system is a little bit quirky. So for today, we're going to really focus in on using the National Weather Service High Resolution Rapid Refresh Forecast Model. You've probably seen quantitative precipitation forecasts from the National Weather Service that look something like this. These are typically 24-hour or 6-hour totals. For our purposes, we wanted to narrow the temporal resolution down some to as much as 1 hour, if not sub-hourly. And this HRR model allows us to do that. So the high resolution rapid refresh model, this is just a screen capture from the National Weather Service website, is issued every hour. It's updated every hour by the Weather Service. It runs 18 hours, sometimes longer, depending on the run. But it's a good tool for short-term weather forecasts in a particular area. So now that we've settled on where to get the forecast precipitation, as an input, we want to bring that into a high-resolution modeling process. So to do that, we need predicted flood depths on a local scale, given the rainfall input. The challenges, as I said before, model complexity, simulation time. How often do you run this model? So the decision you have to make here is to focus on just the key inputs, use existing models as much as you can, and you have to run these pre-event in enough advanced time so that you don't scramble when you get that rainfall forecast to develop a flood depth. And to do that, we generate what we are calling a response surface. So the modeling is pretty traditional. We're applying rainfall to a two-dimensional grid. The model is doing its 2D surface flow to get areas of ponding. In addition, we are incorporating a drainage network into the model. So that's a 1D pipe flow algorithm in the model. And that really combines the surface flow, the storm drain network to get you more accurate flood depths on the surface. This is an example of such a model in action here. The colored areas are the areas of flooding. You might be able to see in the blue lines, that's the storm drain network. And this particular event is a rainfall event a few years back in an inland area that created up to 4 to 6 feet of flooding in this facility. Oh, by the way, this is the FEMA flood insurance map for that same facility. You notice it's in an area of minimal flood hazard because it's distant from the nearest stream. So this goes to show the damages that can happen even if you're not in a mapped floodplain. If you happen to be in a topographic low area, in a relatively urbanized area, these types of cloudburst events can really wreak some havoc. So we've set up the model, but we also need to acknowledge there's more to the response than just rainfall and land use. We can also have a tidal condition like we do in Norfolk, Virginia, like we do here in New York City, where I am sitting right now. You can have blue sky tidal flooding. This is another impact of climate change and increasing sea level rise through the stormwater system or direct flooding. This particular photo shows flooding through the stormwater system. That would really inhibit the amount of outfall capacity you have in a drainage system if there were to be a rainfall event at the same time as one of these high tide events. So this introduces another area of complexity to the model. Maybe you have a small ponding depth for this particular event under a mean tide condition. Under this high tide condition, maybe you have a much deeper area of ponding in this area. So this is another complexity that we want to incorporate into the modeling. The other big one is rainfall intensity. Obviously, 2.5 inches of rain isn't the same if it happens in 6 hours as it would be if it happened in 1 hour, particularly in a very impervious area. So that rainfall intensity also needs to be incorporated into the model. You could keep going and going, but it's really important to limit the complexity because we want to limit the simulation time and we want to limit the modeling effort upfront. So we really want to focus on what's really, really important. And where we want to go is on to this image at the right, which is a snapshot of a hindcast model that we did for a particular rain event that you see in that photograph on the left side. This happens to show the extent of the flood depths and then the roadway network color-coded depending on what the flood depths are on the roadway. So this is the kind of information we want to push out before the event so that people know, hey, avoid these roads in red, ideally avoid the roads in orange too, so that we can avoid folks driving through the flood. And this has a number of different applications. It's not simply a mobility application. If, for example, that wasn't a pizza joint on the left, it was an electrical substation or some other power producer, a critical facility of some kind, you would want to make sure that that facility knew this was coming so that they could take steps to protect their facility, to improve their resiliency, to otherwise adapt, to minimize any sort of disruption to society, to minimize loss of life and property damage. And again, once you have that model running, you can use it to do all sorts of neat stuff. This is just a Google Earth visualization of that inundation layer that kind of shows you the depth against the buildings that we would expect as a result of this event. So that sets up a number of different runs. Once you identify the variables you want to run, you can identify a minimum, a maximum, and then an increment, and this becomes a modeling matrix. Once you have your flood simulation matrix set up, let's talk about what you do with that information. You generate a number of flood simulations. In order to generate, we are calling a response surface. So this is an example response surface, and we're plotting this three-dimensionally in this cube where you have flood depth, which is what you're solving for on the y-axis. You have a rainfall depth on the x-axis, and then the axis heading into the screen is flood duration, and that's representing intensity. In addition, we have a tide condition that we're accounting for. This is the highest tide condition. And the idea is we generate this response surface based on a number of different flood simulations that we are doing, which we are representing here with these red dots. So each of these vertices represents a single simulation that you do in your model. From that, if you connect all these dots, you generate this mesh, which represents the actual response surface. And the idea is by doing a limited number of flood simulations, you can generate the type of relationships needed to predict the response, the flood depth, anywhere along this surface. So for any duration, for any rainfall, for a particular given high tide, you can use this surface to estimate what the flood depth is. You can do this response surface generation for a different range of tide conditions. And again, it's important to focus on what's important here. We're trying to keep it simple by just looking at 4 different tide conditions. Here, we're talking highest tide, high tide, mean tide, and low tide, for example. And to show you an example conceptually how this would work, say we have a forecast of a certain set duration, which you would see here with this dot, and a certain rainfall in that given duration. And that will be generated from the HHR model that we're getting from the National Weather Service. If you also know what the tide condition is, say we have an unfortunate tide condition, which is the highest tide in our simulation set, you can start to connect the dots. So the duration, again, represented on the axis heading into the screen. You have the rainfall, which is represented on the x-axis. And where those connect to the highest tide, represented here in the yellow dot, you can then get that response from your response surface and generate a flood depth. So this is how we take the HRR model, the rainfall duration, the rainfall depth, a set of simulations that we ran before the event to generate this response surface and get an estimated flood depth for that event based on a forecast, so in advance of the actual flooding. So you could do this for any rainfall depth, for any duration, and for any tide condition. And you can do that in a number of different programs. You can code that yourself. You can maybe put a spreadsheet together using Visual Basic to do this. But the idea is to have these surfaces done so that you can be able to predict that flood depth in advance of the event without actually having to do the modeling. The modeling is already done in advance. So what is the future of our process here? The challenge being, this is still a very complex modeling problem. The simulation time is still a problem. It's just something we're doing in advance to generate those response surfaces, but to get there, to get those response surfaces together is still quite the effort. The run frequency, once you do the simulations in advance is not that big of a deal, but the more runs there are, obviously the more complexity there is. So the future direction we see going, and we've had some discussions with various partners about this, is to introduce machine learning and AI into this process. You still have to do some modeling to train the AI. You can't really get out of that, but you can reduce the number of model runs necessary to do a very specific AI training set. Verification and validation is very important, either through instrumentation or crowdsourcing. Once the AI is trained, it can provide some unexpected results. Those unexpected results may or may not be correct. You have to go out into the field and make sure that the AI is functioning as you want it to. Then the artificial neural network regression and classification, that is something I don't know really anything about. But we know we are talking to our project partners who are running these sorts of processes that are important in terms of minimizing the actual upfront effort in getting these response surfaces together. So some of the advantages, again, this is going to drastically reduce simulation time. It automates the process to a degree, and it provides you some flexibility for some future adjustments. You can always tweak the training set. The AI can continue to sort of learn based on the tweaked training set. And hopefully we get some accurate output. The disadvantages of using this process: upfront complexity, modeling simplifications, and accuracy. You do sacrifice some accuracy, at least in today's technology. That may change as we go forward and computing power improves, but you do sacrifice some accuracy because you're not doing as many detailed model runs. So with that, we can start talking about the communication platform, and I will turn it over to Dan Boudreau to do that.
Making the results of the high-resolution modeling actionable in order to support data-driven decisions, visualization, and communication presents its own set of challenges. First, addressing flood response and emergency planning, particularly for a municipality, requires lots of data. Storing and managing that data as inputs for the modeling process and the results needs to be accessible, fast, and efficient. Second, the predicted flooding needs to be compared with assets and facilities to quantify predicted impacts that will likely affect them and turn that into actionable information. Third, presenting the modeling results and impacts in a timely, coherent, and useful way to stakeholders can be a challenge in of itself. GIS provides the capabilities required to meet these challenges. First, the geodatabase is an ideal data container for storing data inputs and results, and provides the performance, functionality, scalability, and flexibility when dealing with large, complex, and dynamic data sets that are used in computationally intensive processes like flood impacts. Second, by employing geoprocessing models and Python code, workflows can be parameterized and automated for analyzing predicted flood impacts against physical assets and facilities. Finally, enterprise GIS can be a platform employed to share and extend this information through web services to desktop, web, and mobile applications to communicate to stakeholders, first responders, and the public. What you see here is a simplified GIS-based data management and visualization framework to support this type of workflow. It all starts with the data. This includes near real-time or real-time observational information collected by sensors, tidal gauges, forecasted atmospheric data, and information reported by the public through mobile apps such as Waze. This is combined with other static data such as LiDAR elevation, hydrologic data, precipitation, and the actual assets themselves that are vulnerable to flooding, such as structures and roadways. In the middle is where all of this data is processed through real-time events using something like GeoEvent Server or Velocity from Esri. This information is used in hydrologic and hydrodynamic modeling, where it can be pushed to AI and machine learning if necessary, or directly over to a geospatial analytical model. By employing AI and machine learning, a set of system response curves could also be developed and then pushed into the geospatial analytical model. That model calculates impacts to assets through a series of submodels using spatial and statistical processes via ArcPy and Python. Further, these models can be automated and run as scheduled tasks. These are published as information outputs as a combination of web services, JSON, and GeoJSON feeds. The web services and data feeds are supplied directly to stakeholders and are displayed in web applications, dashboards, and desktop applications to support additional analytics or planning activities and field operations, and of course, emergency response. Additionally, some content is pushed to mobile applications for use by authorities in the field for reporting events and the status of assets, or even the public through applications such as Waze or Google Maps for mobile devices to assist in navigational requirements in automobiles and such. Here is an example of a map-centric web application which combines dozens of authoritative layers from federal, state, and local sources depicting topography, assets, real-time weather, and incident reports, along with modeled predictive flooding and impacted roadways. This is for an incident on November 11th back in 2020. On the left is information for a particular street, in this case 15th Street, showing calculated or predicted minimum, maximum, and average predicted flooding. Web mapping applications like this one and other dashboards can aid municipalities in managing this information.
So let's leave you with some takeaways, just a handful before we answer your questions. Intense rainfall flooding is difficult to predict in advance. Detailed localized warnings require these innovative approaches. Automating the flood response prediction process is going to be important going forward, and additional innovation research and data is needed to progress. We really hope this talk, which really focused on a generalized conceptual framework, helps to spur discussion in the industry on how we can better respond to these intense rainfall events and the flooding that is resulting from them, so that we can fill a gap in climate change resiliency, because I think this is one of the more pressing problems that our industry is facing. How do we respond, short of digging up our entire storm drainage systems, to help people, communities, and businesses avoid flooding impacts as a result of very difficult to predict cloudburst or rain bond type flooding? So thank you for listening today. And with that, we will be happy to answer any of your questions.
Thank you, David and Daniel, for talking about how to deliver urban flood information on demand. We have some questions, so let's jump right in. The first question is, how do you integrate the model in the transition of 1D to 2D areas? Right,
so I can handle that one. So typically what we do is we rely on the model to do that itself. So we stress using coupled models that have the two-dimensional and one-dimensional aspects built into them. And I know we have another question that get into which models we utilize to do that. So maybe I can answer the second part in the next question.
Okay, real good. Tom wants to know that he's very impressed by the system. What models are utilized for overland flow and pipe network modeling?
Right. So this is an area where there are more and more candidates to use. Historically, a lot of the storm drainage type models that folks use were strictly one-dimensional, where they operate on a catchment basis and then route that flow into the pipe. But more and more of them use a two-dimensional surface algorithm that is internally within the model coupled to the 1D pipe flow. So we use several of them, including SWIM, ICPR4, Flow2D plus SWIM. There's any number of them out there. We don't particularly endorse one or the other. There's several good candidates that you can look to do some Googling and pick the one that fits your particular problem, depending on the site.
Great. I think the urban flood modeler is the second part of that first question. What model did you use to simulate the cloudburst in New York City? Can you talk about the instability issues and the lessons learned while modeling the stormwater spaghetti?
Yeah, that's a really good phrase, stormwater spaghetti. I'll have to remember that one. So for the New York City work, we are generally using ICPR4, which is one of the smaller 2D, 1D pipe flow models. We do enjoy using that one. There's a lot going on in parts of the city that we model. There's a shallow groundwater table. ICPR4 is able to also incorporate groundwater into the modeling. So when you're doing some of these nature-based solutions that rely on infiltration, it's helpful to get the groundwater component in there. That's a whole other talk for a whole other day. So that's basically it. I'll leave it there because I know we're kind of short on time.
Okay, let's see if we can slip in our last question. Would ML and AI be helpful in learning and doing some of the mundane GIS post-processing, as well as incorporating satellite info? High water marks, observations, etc.
Yeah, I'll answer that question. Certainly, machine learning and AI could play a role in some of this. I mean, currently our modeling is actually comprised of several submodels that process data coming in at predefined time intervals, and those models are built, as I mentioned in the presentation, built with Python and built within ArcGIS, and so they just run automatically, and they just process that data as it comes in, and then spits out the outputs as published map services and feature services. But some parts of that we could incorporate machine learning. We are actually looking into employing that in the future.
David and Daniel, thank you again. And the audience, great questions. And we're going to jump right into our final presentation, Urban Flooding Open Knowledge Network, delivering flood information to anyone, anytime, anywhere. Venkatesh Merwade is the presenter. He is a professor in the Lyell School of Civil Engineering at Purdue University, where he has been since 2006. During 2004-2006, he worked as a postdoctoral fellow at the Center in Water Resources at the University of Texas, Austin. Dr. Merwade received his Bachelor of Engineering in Environmental Engineering from Shivaji University in India, an MS in Engineering Hydrology from National University in Ireland, Galway, and in 2000, and a PhD in Civil Engineering from the University of Texas, Austin. His research and teaching interests include surface water hydrology, with specific focus in flood modeling and mapping. Thank you, Venkatesh, for the excellent, thank you, Venkatesh, for agreeing to speak with us today, and you may start.
Thank you, Meg.
Hello, welcome. My name is Venkatesh Merwade, and I am a faculty in the Lyell School of Civil Engineering at Purdue University. I'll be talking about Urban Flooding Open Knowledge Network, and the goal of this project is to deliver flood information to anyone, anytime, anywhere, and in short, we call this UFOKN. This project is funded by the National Science Foundation, and it is led by Lilith A. Ghiazarian at University of Cincinnati, and I'm one of the co-PIs on the project. And as you see on this slide, it's a very diverse team, and it includes partners from academia, nonprofits, industry, federal agencies, national labs, states, counties, and municipalities. So let me just talk about why we are doing this, and then we will go into what we are doing. So what you see on this slide is familiar to many of us, and many of us have lived through them. And this is what happens when cities flood. And what you see here is a series of failures propagating through urban infrastructure and communities. High winds take down the power grid and cities plunge into darkness. Power failures disable pumps and valves within the combined sewerage system, and then raw sewage backs out into people's homes, creating public health hazard. Similarly, wastewaters overflow into streets, combine with existing stormwater runoff, and they flood buildings and rendering the roads and bridges impassable to traffic. Same power outage may disable operations of the drinking water system, and then people cannot access clean drinking water at this critical time. Highways also flood, and then these highways become waterways, and then we cannot even go to a store to buy any food items or anything that we need during this critical time, and neither can we evacuate during these hazardous times. So for example, when we are flooded, we cannot evacuate, the streets may be also flooded. And we know that floods and other climatic events that cause flooding were the highest among all disasters in the last century, as you see on this pie chart on the left. And what you see on the right is that economic damages and corresponding fatalities have also been increasing due to floods. In 2017 alone, the cost topped 60 billion. So the question is, despite all this work and research that we have been doing, we still cannot predict how flooding impacts cities and how failures will cascade. And why is that? And to answer that question, we should understand how complex urban environments are. So cities are very complex systems, and they include multiple layers of infrastructure, including transportation network, power grid, water systems, civic infrastructure, groundwater, stormwater, and wastewater systems, and so on. And we call this as urban multiplex, as you see on the left here. And all these systems are interconnected, and they are also intertwined with socio-economic and public health sectors. So everything is complex and everything is interconnected, and when one system gets impacted, that impact propagates to other systems, and that is what we are not able to simulate. And the reason for that is, when we are trying to address these problems, we are working with data and simulation results from models. So we know that in physical reality, all these systems are interconnected, but the data that we are using and the simulation model output that we get, none of these are interconnected with different systems. And that is why we cannot predict the cascading failures and the total impact of floods on cities. A manifestation of this lack of data connectivity is what you see when you try to do an internet search flooding near me. So we did this search from Santa Barbara, California in 2020 using Google, and you see the Google results on the left. And we also did this using Bing, and you see the results for Bing on the right. So what you see here is that these results are 3 years off and half country away. So for example, you see reports from 2017-18 flooding in Texas and Midwest. And so there is no temporal or spatial scoping of flood responses, rendering them irrelevant and inactionable. So whenever there is a flooding, and if you try to find information related to that, you really cannot do that currently using Google or Bing or any other search engines. So to solve this problem, what we are trying to do is we have developed UFOKN, which again stands for Urban Flooding Open Knowledge Network. UFOKN is an information infrastructure built on top of modern search engines like Google or Bing. It links real-world infrastructure that you see on the left here to dynamic flood predictions on the right. And the result is that now UFOKN represents the relationship within connected urban systems and links them to flood forecasts. In addition, UFOKN is extensible in future for any flood forecasting model and any new infrastructure with their own cascading impacts on the cities. So a city may have multiple models. You can bring all these models into UFOKN and you should be able to use those results and also connect those results with the actual infrastructure so you can understand the cascading impact. So it is scalable and extensible. So essentially what we are striving to accomplish here is to develop a technology that will provide meaningful information when you type flooding near me in any search engine. It will produce spatially and temporally relevant information on emergency guidance. It will tell you about local road closures. It will tell you about available shelters. It will give you warning about flood, and it will deliver it to you on your fingertips. And this is the future that we envision for flooding. So for example, on the left, you see the links that can be useful during this emergency, and on the right, you can see a spatial map of what is happening, and you can see a person here, and that is to show how deep the flooding is, and that will give you a real sense of what the danger is when you try to go out during this situation. So this is what we are trying to do. Then the question is, how do we go about it? So what we did was we started out with 2 user workshops in 2019 and 2020 with a total of 80 participants. And these participants came from different agencies that are involved in flood management, so emergency responders, city planners, city managers, municipalities, and so on. These workshops employed human-centered design to make sure that UFOKN was not only viable but also useful in practice. So we wanted to hear from our potential users on what they want, and we wanted to incorporate their needs into the UFOKN. So from participants' feedback, we grouped our users into what we call personas. You see here an urban planner, you see emergency response manager, you see federal employee, and so on. These personas serve as proxies for all the real users from our workshops, and they capture details about the scenarios in which these personas want information from the UFOKN. These details, such as their traits, goals, behaviors, pain points, and needs, helps us make design decisions for how UFOKN information should be uniquely delivered. For example, we learned from Emergency Erica that she makes quick and adaptive decisions for fast, efficient deployment of first responders. Her pain points are not having timely and accurate information as she manages the response. She needs real-time flood forecasts of both the flood extent and its depths. Erica profiles helps us ensure that UFOKN is effectively delivered to emergency manager within their real-world experiences. By building out more portraits across 7 other personas, Phase 1 helped us identify potential customers and how the UFOKN can positively impact their roles. So using the feedback from the workshops and developing these personas, what we are trying to do is we are trying to create a UFOKN that is scalable, operational, and sustainable. It will be used by a variety of users, including our partners and stakeholders, to obtain flood-related information through their device of choice. Here you see just some examples of how UFOKN will be used. So for example, buyer Bob on the top left is a potential homeowner, and he is checking flooding history in his neighborhood. Bob will find out how many homes have experienced flooding in the recent past and when. Similarly, a private citizen, we are calling this person as Nervous Norman on the right. He may be using a smartphone to find a safe driving route during a flood. Similarly, emergency response manager, emergency Erica on the bottom left, could interact with UFOKN through her computer to find areas that are at flood risk. So as I mentioned, we are trying to create a scalable UFOKN for the entire nation by starting with some pilots, and we plan to scale it to the continental US. The fully scaled UFOKN will integrate urban multiplex information, provide actionable flood information, and help reduce human and economic flood losses. So what I would like to talk now is, now we know that why we are doing this and what we are doing, what functionalities do we have. So this is how our current UFOKN app looks like. And what you see here on the top are 4 tabs. So the first one says FEMA, the second says risk point impacts, the third says heat maps, and the fourth says data table. So let's talk about the FEMA flood risk mapper. So the FEMA flood risk mapper tool links urban infrastructure information to flood maps corresponding to different return periods. And right now, all this is static information. So there are maps corresponding to different return periods. So what you can then do is using those maps, and what you see on the bottom left here is a spatial data set that you can provide. So in this case, it's a census block data set. So you can click on any census block, and then within that census block, you will see how many homes. So in this case, we are looking at buildings, power stations, road network, and urban storage tanks. So how many of these are at risk within that polygon that we chose? So in this case, we chose the US Census block. So basically, you can find an estimate of the flood risk across any infrastructure delivered from pre-generated maps, such as this FEMA 100-year risk map, and you can also go back historically up to 30 years. And whatever flood information is available, you can use the risk mapper to do that. In addition to visual interpretation, you can also see how many buildings are at risk, how many roads and underground storage tanks, and then the total risk points within that query that we used. The next is risk point impact. So this goes into a forecasting mode. So what we have here again is the same background map with risk points, but now we can see it in forecasting mode. So for example, we are using a model called ICPR, and we have ICPR, we have National Water Model. If a model exists for that area, that model can be incorporated. So you go pick a date and time and see what is going to be the forecast for that particular area, and then it will show you for any given location, it will show you what the past was and what the near future will be going into the time scale that you see here. And in addition to that, it will also show you what the depth will be, and depending on that depth, you will see the color of this person changing from green to red. So green means the depth is not very high. If it is red, it is at a risk level. So you can see right now the depth is higher than 2 feet, which means the home will likely get flooded, so it is not safe. So this is the interface that we can use in forecasting mode. As I mentioned, we can have any number of models here, and we can see what forecast each model is giving, and then we can make a decision on whether to evacuate and all that. The next option that we have here is heat map. So in the previous interface, you can look at each individual building or location. So in heat map, you get an aggregated view of what is happening. So instead of giving you information for each home or each building, you are getting information within a neighborhood. So again, you can pick a census block or any other spatial polygon that you want to use, and within that polygon it will show you which areas are at risk, and that information can be used by emergency Erica to decide which area to evacuate first and where to allocate funds and so on. And what you see again here is the aggregation level, so you can change the aggregation level, and based on that you can get a different view of this heat map. And finally, you can also get all this information in tabular format. So once you figure out visually what is happening, then you can use these different criteria. So for example, you can say, give me all the locations that are going to have a depth between 2 feet and 14 feet. Then it will figure out all those buildings that will satisfy that criteria. So we said buildings. Instead of building, you can also pick power stations, roads, and underground storage tanks. So those are the classes that we are working on currently. But in future, those can also be categorized into schools, hospitals. So whatever number of risk points you want to include, we can do that. So we are including buildings. So within buildings, as I mentioned, so we picked single family home. And then you can say within, so Wildwood Pines Lane, so within that lane, give me all those buildings that are within 2 to 14 feet of water, and it will give you those locations. And again, you can get that information and you can print this out and give it to an emergency responder, and they can go and evacuate those people. So these are just some of the applications that we have currently developed, and we'll be expanding these applications as we go along. We are also working on a flood notification and reporting tool, and that will allow users to sign up for location specific notifications or daily reports using a customized framework designed to be adaptive to the device of choice. It would incorporate easy to use interfaces for generating early warnings and live on the ground information. The UFOCAN flood prediction and forecasting will be an extensible framework. We are building capabilities to ingest national water model forecasting data and directly run different area specific models. In addition to national water model, our research and development group is working on bringing in other high resolution storm forcing models to drive flood prediction. Therefore, the UFOCAN can integrate probabilistic, historical, real-time and forecast information from any flood model and integrate the information with its knowledge graph. So that way it's model agnostic, and it can give you information from the best available model or any models that are available for that particular area, and the decision maker can then pick what information to use. We are also working on critical infrastructure vulnerability assessment tool that would identify vulnerable areas and critical locations like schools, hospitals, Superfund sites, and provide risk propagation estimates. For example, the tool would identify the downstream impacts to all urban infrastructure due to the failure of an EPA water quality site. This can be pre-computed or quantified on the fly for a forecasting model. The utilities and operations management tool can help in better management of power systems during flood events by providing the risk of failure due to flooding. This tool would provide warnings and notification based on user-defined triggers and provide the risk of power loss across residential communities due to substation failures. The UFOCAN can handle sensitive data using its licensing functionalities, and the user can choose which information to share and which information to keep private but interact with the knowledge graph. The tool can also provide trigger warnings if any pre-stored evacuation routes are at risk of inundation. Zonal maps of shelter locations can also be embedded in the graph to identify alternate safe routes in case the evacuation routes get flooded. There are other tools and functionalities not covered in this presentation that are also being developed to improve how users share, ingest, and analyze the risk to infrastructure due to flooding. So I hope you got a flavor of what EO4KN is, what its current capabilities are, and what we plan to do to address risk associated with flooding and how we can capture and provide information associated with cascading impacts from urban flooding. If you want more information, you can go to eo4kn.com. And if you want any other specific information, you can either contact me or the lead PI, Lilith A. Gazarian. As I mentioned, this is a collaborative project funded by NSF, and we have lots of partners working with us, including the National Water Center, U.S. Army Corps of Engineers, EPA, USGS, FEMA, and several state and local partners. So thank you very much for your attention. And as I mentioned, you can find more information at eo4kn.com. You can also follow us on Twitter. You can email us. And I look forward to chatting with some of you during the presentation and discussion time. Thank you again.
Thank you, Venkatesh, for that excellent information. We do have some questions, so let's get right to it. The first question, since a significant number of people depend on social media for information, does UF-OKN, does that project connect or get data from social media as well?
So that's a very good question. I see that coming from Shish Koirala. So thank you, Shish, for that question. So as you saw in the presentation, so we are currently prototyping based on our personas and partners. Right now we are working with Lee County in Florida. So again, these are the people, they don't depend on social media. So depending on the partners, so the short answer right now, we are not using anything from social media or publish anything to social media. But once we start working on some prototypes for, let's say, a persona, buyer Bob or nervous Norman, individual homeowner who can take decisions on their own and if they depend on social media. So if we have a use case for that, then we'll explore that. So right now we are not connecting with social media.
Okay, we have two questions from Alicia, and the first one is, what is the schedule for scaling to the nation? Or is there something I can use today?
Yes, and I think the answer will connect to the second question that Alicia asked, has this been prototyped on a specific community? So yes, currently you can use it for Lee County in Florida. We are prototyping it, so we don't have something like working in real time, but we have been using historical data. So we have data for Hurricane Irma. So you can go back and use the app and look at forecast during Hurricane Irma, how many floods, how many homes will get flooded, buildings will get flooded, how deep the water will be, and so on. So based on the examples I showed you, you can try all of them out for Lee County in Florida. And in terms of going national, so we are interacting with the national water model, which is at the national scale. So technically, yes, we can do this for the whole nation, but right now we don't have our app displaying results for the whole nation. So right now we are working on few counties in Florida, and then we are also thinking of doing some areas in Texas.
Okay, so I think that also answers Joe's question about, is there any community in the US using this system? Our final question is from,
maybe let me just answer.
Okay.
So is there any community utilizing? So right now they are not utilizing, so we are developing the system. And once we develop the system, we'll work with the partners, and that's when it will go into operation. So right now, nobody is using this for making decisions. So the goal is to produce a product that people can start using.
Great. That'll be exciting when a community has that tool. Do you plan to test and evaluate this concept framework in terms of interoperability, data synchronization from the cloud to users? And that's from Victor.
Yeah, so again, thank you, Victor. Yes, so we are testing it, and the system is working with data sets from multiple models, multiple resources. So in that way, it is interoperable. So I think the short answer to your question is yes, we are doing that.
Okay, that's all the questions we have. I want to thank Venkatesh and all of our speakers today for this session. It was full of good information on flood warning systems, and we appreciate your willingness to share your information. This will conclude our session on modeling for flood warning systems. We'll now have a 30-minute break, and we hope that maybe we can take some time to visit the exhibit hall and talk with the exhibitors and our sponsors. Then at 11 o'clock Central Daylight Time, the plenary session on social and environmental justice in managing flood risk starts. Please join us then.